This is the solution for problem 95 from chapter 17. The tire has a weight of 30 pounds and a radius of gyration of 0.6 feet. If the coefficients of static friction and kinetic friction between the tire and the plane are 0.2 for static and 0.15 for kinetic, determine the maximum angle theta of the inclined plane so that the tire rolls without slipping. So if the tire rolls without slipping, then we are at the maximum value for the force of static friction. I have drawn a free body diagram for the tire, and I'm going to apply Newton's second law in the x direction and also in the y direction, but I want to use a tilted coordinate system here and say that the x direction is parallel to the inclined plane and the y direction is perpendicular to the inclined plane. When I sum up the forces in the y direction, I have to break the force of gravity down into components. If this angle is theta, then this angle is also theta. So I have a component for the force of gravity, mg cosine theta, which is pointed in the negative y direction. That's equal to the normal force. Because the normal force is perpendicular to the surface of contact, it is pointing in the positive y direction. So I have this equation here. I have a force of static friction, which is pointed in the positive x direction, and that's going to cause rotation like this. The sum of the forces in the x direction is equal to the mass times the x component of the acceleration of the mass center. The tire is accelerating this way, so that would be acceleration in the negative x direction. So to keep things straight here, I'm going to say it's negative agx because it's pointed this way. Because it's rolling without slipping, that's equal to the radius times the angular acceleration. And because I put the negative sign in here, that acceleration now, angular acceleration, should be positive. So when I sum up the forces, I have mg sine theta, that's the sine component pointing down, which is the negative x direction, plus the force of static friction pointed in the positive x direction, is equal to m times the x component of the acceleration of the mass center, and the mass times negative r alpha is what I get for that. Then I can sum up the moments about the mass center. That's equal to the moment of inertia about the mass center times the angular acceleration. Because they gave me the radius of gyration for the moment of inertia, I say that's the mass times the radius of gyration squared. So that's mk squared times alpha. And for this sum of the moments about point G, I get 0 for the normal force. For the force of static friction, that would cause rotation this way. This distance is r, so that's r times FSF for the sum of the moments. And that's equal to what we had here. And then this is equation 1, and this is equation 2. I want to combine them. And if I look at what I have on the right-hand side of equation 1 over here, that's mr alpha. So I'm going to solve this for mr alpha, which I can do by multiplying both sides by alpha and dividing both sides by k squared. So that gives me mr alpha is equal to the force of static friction times r squared divided by k squared. And then I can take this equation here, multiply on both sides by -1, so I get mg sine theta minus force of static friction, and then put this in for mr alpha, and we get this equation here. And I can bring the two terms with the force of static friction over to the same side, and that gives me this. Pull out the force of static friction. I have, this is 1 on the other side, and this is r squared over k squared, so that's r squared over k squared plus 1 times the force of static friction is equal to mg sine theta. Now, because we were asked to find the maximum value for the angle, we must be at the maximum value for the force of static friction, which is the coefficient of static friction times the normal force. The normal force is mg sine theta, so that's coefficient of static friction times mg cosine theta, then times what we had here, r squared over k squared plus 1 is equal to mg sine theta. You can cancel out the mg's, and then divide both sides by cosine. Sine over cosine is tangent, and so tangent of the angle is equal to the coefficient of static friction times r squared over k squared plus 1. Then if you take the inverse tangent, you can find the angle by plugging in the values that they gave you in the problem. So if you do that, you get 46.88 degrees. But the reason that I did this symbolically is so that now we can look at what happens as if, or what happens if, for instance, the radius of gyration increases. So if you increase the radius of gyration, then r squared over k squared is going to be smaller. So you'd be taking the inverse tangent of something smaller, which would give you a smaller angle in this situation. So as k increases, the maximum angle for which the tire can roll without slipping would decrease. If you increase the coefficient of static friction, then the maximum angle is going to increase as well. And if you look in the back of your book, instead of a tire, if you had a ring, for the thin ring rotating about its center of mass, you have mr squared, which means because for the radius of gyration, you have m times k squared. For the ring, r and k would be equal to each other. And if you look at what we have here, if r is equal to k, then you have r squared over r squared, and that would be 1. So it would be the inverse tangent of the coefficient of static friction times 2 if it was a ring instead of a tire. And that concludes problem 95.